In this section, we will study pinhole camera and perspective projection. They represent the projection from 3D scene to 2D image using geometric and mathematical models. A pinhole camera may be described as a black box. It has a hole on one side and a photographic film is placed on the opposite side of the hole. The hole is called apical center of the camera. Distance between apical center and the photographic plate is called the focal length. Light may enter in the box only from the apical center. Axis lines marked with X, Y, and Z are shown in the figure. The line passing from the center of the camera towards the object is called Z-axis. Horizontal and vertical direction are considered X and Y axis respectively. Reflected light rays from the object passes all the way from the hole to the photographic film. The light rays travel straight in a line and bend in an inverted image formed on the photographic plate. Larger objects appear larger in the image. Object 1 shown in the left is comparatively larger than the object 2 shown in the right setup. So the left image is larger than the right image. Similarly, size of the object also depends upon the distance from camera. Here object 1 and object 2 have the same size, but distance of object 1 is comparatively less than object 2. So left image is comparatively larger than the right image. Perspective projection is corresponding mathematical representation of the pinhole camera. It simulates the way how camera and human eye perceive depth mathematically. One important concept related with the perspective projection is perspective distortion. In real world, parallel lines seem to converge to a point called vanishing point as lines travel away from the camera. The effect is called perspective distortion. Let's discuss the geometric transformation, the operation that modifies a special relationship of the pixel in an image. These transformations adjust the position, orientation, or scale of the image content while preserving its appearance and structure. First of all, we discuss the translation. The translation moves a point along the axis. The motion can be along the x-axis or the y-axis, or it may be simultaneously between x and y-axis. There is no change in the size, just point is moved along the axis. Next is rotation. In rotation, given point is rotated with respect to region with a certain amount of theta. In scaling, the size is changed. The change depends upon the scaling factor. If scaling factor is greater than 1, size will be decreased, as shown in the bottom figure. And if scaling factor is greater than 1, then the size will increase, as shown in the upper figure. And if the scaling factor is 1, there will be no change in size. Scaling factor may be different along the x-axis and the y-axis. Sx in the matrix represents the scaling along the x-axis, whereas the Sy represents the scaling factor along the y-axis. If value of the both factors is same, then the scaling is called uniform scaling. Otherwise, if the size is different, the scaling is called non-uniform. Next comes the sharing. Sharing shifts the pixels of an image along one or more axes. Just like scaling, sharing is controlled by corresponding sharing factor. Next geometric transformation is reflection. In reflection, pixels are reflected around the axis. We may shift, reflect along the x-axis or y-axis or both along the simultaneously along x and y-axis. Corresponding mathematical matrix operation are shown in the figure. Let's discuss the homogeneous coordinate. In homogeneous coordinate, we add an extra dimension to the Cartesian coordinate. This results in uniform representation of our transformation. Homogeneous coordinates allows us to represent translation, scaling, rotation, and other geometric transformation using matrix multiplication. In Cartesian coordinate, translation cannot be represented as a matrix multiplication. But with homogeneous coordinates, it can be easily done by using a 3 by 3 matrix in 2D systems. By introducing an extra dimension, all transformation, whether they are linear or affine, can be combined into single matrix operation. This simplifies the composition of multiple transformations into one. Homogeneous coordinates enable perspective transformations such as those found in camera models and allow for the representation of points at infinity, which is useful when handling parallel lines in 3D scenes that converge at a vanishing point in an image. For basic operations using homogeneous system are shown in the figure. It can be seen that translation operation can now be represented by um, multiplication operation, shown in the top left. We may combine two or more operations in a single matrix. We may multiply two or more corresponding matrices ahead of time and then use the resulting matrix for final calculation. The combined matrices are called composite matrices. This reduces the calculation time at runtime. And the question is, does the order of the matrix operation matter? Yes, it does. In the left figure, we are performing translation and then rotation, whereas in the right image, we are performing rotation first and then translation. The results are different. We have presented the operation for 2D only. They may be converted to 3D by simply adding another axis, the z-axis. Translation and rotation matrices are shown in figure. Similarly, we may represent rotation along different axes with corresponding rotation matrix. Often all of the three matrices are multiplied to calculate the effective rotation matrix.